Hello, hello. This is a little bit of review from what we've discussed before, and then about a bit about cardinality. So remember that cardinality of a set is it's a relation that allows us to compare sizes of sets. And so if you look at, say, set A and another set B, we say that the cardinality of A is less than or equal to the cardinality of B if there's an injection. Remember, that means a one-to-one function from A to B. And it turns out you can prove that's the same thing as being able to find a function that going from B to A that's onto or a surjection. And so we have two ways to characterize that, but both of those are kind of, if you think you can put A into B in a one-to-one manner, it makes sense that A is no bigger than B. And if you can plaster B all over A, it makes sense that B is at least as big as A. And then we had our some basic facts we can look at. For instance, the cardinality of a set is always less than or equal to itself. You could use the identity function to show that. Since a one-to-one function composed with a one-to-one function yields a one-to-one function, that gives us this next relation that if A is no bigger than B and B is no bigger than C, then A is no bigger than C. Then the last one is tricky. This property is called anti-symmetry, and we have the Cantor, Schroeder, Bernstein theorem that says that if A is no bigger than B and B is no bigger than A, then A and B have to have the same size. And again, that's the first one that isn't really trivial. So let's, I'll point you again to this handout that we had, and say if you want to look at the proof of this theorem that's here, you can see that if you have A and B are no bigger than each other, then you get injections F going one way and G going the other way. And then we inductively define this collection of sets called S, and called SNs, and then take their union to be S. And then we can define a function, and I'll let you follow through that proof if you want to. It's kind of an interesting little proof. Anyway, that allows us to conclude that we have this anti-symmetry among cardinalities, and that if A is less than or equal to B, B is less than or equal to A, then A equals B. And so cardinalities are totally ordered. So if you have two sets cardinalities, one is bigger than the other and or less than or equal to the other, and that this less than or equal to behaves the way we're used to less than or equal to behaving. Okay. Next is we have this term countable. A countable set is one that's no bigger than the natural numbers. And so we denote this with the Hebrew letter aleph null, which I have terribly drawn in this way. Okay. By the way, countable, you have to be careful when somebody uses that term, as we mentioned before, because sometimes people mean countable only to mean countably infinite. That means the same size as the natural numbers. More broadly, a lot more people use countable to mean that the set is no bigger than the natural numbers, so they would include finite among their under the umbrella term of countable. So usually context makes it clear. So again, if somebody says countable, be careful. They may mean countably finite, or they might mean countably infinite. If you can put a set in a one-to-one manner, in a one-to-one correspondence with the natural numbers, or if it's finite, then obviously we can list the set, right? Because you take the element associated with 0 and then 1 and then 2, etc., and you'll have a list. So this is countably infinite is the smallest kind of infinity. And again, these are sets of this size are ones that you can list off. And then we talked about a bunch of examples. The natural numbers are by definition countably infinite. And then also the integers are countably infinite. and the rational numbers, right, ratios of integers are, ordered pairs of integers are, the even numbers are. In fact, we could justify some of these statements if you turn to that, and now I have it posted, this preprint of a paper, hopefully soon be published with Mike Bosse, the types of infinity paper. And so here's a little bit about cardinalities. Right here, we have a justification for why, at the bottom of the page, for why the natural numbers and integers have the same cardinality. This, I'll skip ahead. This picture right here shows why the ordered pairs of integers form a countable set. Because notice, if you start off at the origin, you can spiral out, and that will give you an effective means of listing off all of ordered pairs of integers. And again, remember, if you can list something off, that means it's countable. And then coming back up here, if we can do the same kind of thing with rational numbers. So think of the ordered pairs, as we had before, now as ratios. And if we've already run into our rational number, we'll just skip over that, the corresponding dot. But anyway, if we use this, you can see there's an effective means of listing off all of the rational numbers. And so maybe counterintuitively, but it is true that the rational numbers have the same cardinality, the same size as the integers, which is kind of interesting. Okay, but stranger things are true. All right. We also showed before that this theorem of Cantor, so I'll briefly mention this again, that a set is never the same size as its power set. It's always strictly smaller. And so when we write less than means that you are less than or equal to, but you are not equal to. And so that means that while there is an injection from A to the power, its power set, there is not a surjection. There's not a bijection. And so remember, bijection means one-to-one and onto. Surjection is onto. If we had an injection from A to its power set, and we also had a surjection, if we had a surjection, an onto map, that would mean that the power set is less than or equal to the size of A, and Cantor, Schroeder, Bernstein would say that there has to be a bijection. So to show this result, what we're going to do is first show that there's no onto map, no surjection, and then we're going to show that there is in fact a one-to-one map. There is an injection. So the first part shows that A is not as big as its power set, and then the second part says that it is in fact strictly small, that it is smaller. If we look at the proof, it involves creating this rather strange collection. So we say start off with a map from A to its power set, and then say, okay, let's find the set of all, look at the set of all things that are, way to explain it, you look at f of x, right, which, since we're mapping to the power set of A, f of x is a subset of A, okay, because it belongs to the power set. And then we're going to take all of the elements who don't belong to the set that they mapped to. Okay. So B is the collection of everybody that doesn't belong to the set where F mapped them. Okay. And so if then we can ask the question, is this set actually in the range of F? And so kind of focusing here on this line, notice that if capital B were in the range, meaning some little b mapped to it, then we could say, okay, well, if B was in it, little b was in capital B, that would mean that B belonged to F of B, because capital B is F of little b. But if we go back up to the definition, what does it mean to belong to B? It means that you don't belong to where you mapped to. So by definition, B would not belong to f of B, but hold up, that means that B would not belong to capital B. Now going the other direction, what if B didn't belong to f of B, right? Well, if B doesn't belong to f of B, by definition, over here, that means that little b belongs to capital B. That's because that's what it takes to belong to capital B, is that you don't belong to where you mapped to. But capital B is little f of B. And so you can see that if B belongs to capital B, then it doesn't belong to capital B, and vice versa. That's a contradiction. And so the only way out of that contradiction is to pop back up here and say, well, it must be that nobody mapped to this set. And so that means that this guy is not in the range of f. So f is not an onto function. And since it's not an onto function, this means that A cannot have the same cardinality as a power set. And then as a quick little addendum, notice that it's very easy to see that A is no bigger than its power set, because you can always just define the mapping where you send A to its singleton set, the set that just contains itself. And that's certainly a mapping from A to its power set, and it is quite clearly one-to-one. Remember our standard format for a one-to-one proof. Suppose outputs are equal, then show that inputs are equal. And if you can do that, that establishes that the map is injective, or in other words, it's one-to-one. Okay, so I think at this point we've kind of caught up to where we were before a very long break. I wanted to mention some other interesting stuff, namely some cardinal arithmetic. So one asked the question, kind of, how should we define these things? And so I'm going to define cardinal addition, multiplication, and exponentiation. And above you have their definitions, and we have a little bit of a theorem I want to mention. But here, let me kind of explain why these definitions makes really reasonable sense. So what if you had the set like 1, 2, 3, and you union that with the set 1, 2? Okay. So first of all, I want to talk about the size of 1, 2, 3 plus the size of 1, 2. Well, if you make sure that these sets don't overlap, so let's prime these two guys. So I've now made these sets disjoint. If I union them, I now have 1, 2, 3, 1 prime, 2 prime. So notice that we had 3 things in this set, we had 2 things in that set. When we added them together, as long as we made them disjoint, we end up with 5 things. And so if you take the disjoint union of 2 sets, that will give you what we're going to define to be the size of the 2 cardinals added together. Now, I'll mention, we've not really dealt with disjoint union before, so I'll kind of mention an easy way to make 2 sets disjoint is Cartesian the first one with the set 0 and the second one with the set 1. If you do that, then you will end up with the first set has first coordinates in A and second coordinate 0, and the second set has first coordinates B and second coordinate 1. And so those sets don't overlap at all. And so that gives you one way to make things disjoint. But anyway, how about multiplication? Well, what if I took, say, 1, 2, 3 and looked at the Cartesian product of 1, 2? Right? Well, notice here, now we have first coordinate can be 1 and second coordinate 1. The first coordinate can be 2 and second coordinate 1, and etc. And if we finish listing off all of these possibilities, notice that we had 3 things and 2 things, and when we took the Cartesian product, we get 6 things. And you'll find out very quickly, for any kind of any kind of finite set, that this cardinal arithmetic is doing exactly what we would want addition and multiplication. It does work out that a set with m things and a set with n things, disjoint union will give you a set of m plus n things. And a set of m things and a set of n things, Cartesian product will give you a set of m times n things. By the way, if you take a set and Cartesian product with the empty set, remember this is all things whose first coordinates come from A and second coordinates can't be anything. Well, that's the empty set. And so we also see that if we multiply by 0, we get 0. Again, this all works exactly how we want it to. The third one maybe requires a little more thought. Let's think about okay, why does exponentiation go with a collection of functions? So again, we're defining cardinal exponentiation. The size of a to the size of b power is the size of the set of all functions from b, the exponent, to a. Again, let me give you a finite example to see why this makes sense. So what if I take the set 1, 2, 3 to the set 1, 2 power? What do we mean by this? Well, we get a bunch of functions, and maybe I'll try to find a reasonable way to denote them. So for each function, I have to tell you where, too big of a brace there. Let me tell you, I need to tell you where does 1 go and where does 2 go, right? Because our domain is the set 1, 2. Well, I have 1 can go to any of those 3 choices. So for instance, I could send 1 to 1, and then 2 can go to any of those 3 choices. So I could maybe also send 2 to 1, right? That's not a 1-to-1 function, but it's a perfectly valid function. And then the next time, let's see, I could maybe send the first guy still to 1 and the second guy, now I'm going to send to 2. And then maybe I'm going to send the first guy still to 1 and the second guy, now I'm going to send to 3, right? Now I have listed all of the functions that send the first guy 1 to 1. And then ... And if you work through that, you could then look at, there's going to be 3 functions that send 1 to 2 and 3 functions that send 1 to 3. And in the end, we had 3 possible outputs and 2 inputs. Each input had 3 choices that we could make. And so there's 9 total functions. And so notice that, again, this matches up, at least for finite sets. You can show that if you have a set of m elements and a set of n elements, then the collection of functions from the n elements to the m elements will be m to the n of those functions. And so that way of defining exponentiation really does match up with what we want it to. It's always, I think, at least I find it instructive to consider weird cases. How about a to the empty set power, right? This would be all functions from the empty set to a. Well, how many functions are there like that? Well, remember, there's only the empty function, right? Because we have nowhere for anybody to go. Well, we have nobody to send anywhere. So there's one function that does that, the nothing function, the empty function. And so it's the collection of all functions from the empty set to A. Well, there's only the empty function in there. That's 1, which matches up really well with what we want, right? We want something to the 0 power to be 1. Another extreme case would be, what if you were going into the empty set? And so in this case, if A is non-empty anyway, there is no way to map A into the empty set, right? Because a function has to send everybody in A somewhere, and there's nowhere for them to go. And so we just found out that this guy's size is 0, at least under the assumption that A is the empty set, we also have the weird cardinality convention that 0 to 0 power is 1. Maybe we shouldn't, we should kind of worry a little bit about stating that emphatically. Just know that if you're dealing with cardinals, it is the case that 0 to 0, instead of being indeterminate, 0 to 0 is in fact 1. But don't use that fact in like a calculus course or anywhere else. That's specifically dealing with cardinality arithmetic, although that convention's used a lot of other places too. Okay, another, so kind of coming back to addition multiplication, it turns out, except for the finite case, that when you add cardinals, it actually is kind of boring. The bigger set always just swallows up the smaller set. So if you add two large sets together, two infinite sets together, the bigger infinity wins. And maybe surprisingly, and the second one's a bit trickier to prove, but if you multiply, I should have this written in terms of multiplication there. If you multiply two cardinalities, then the cardinality of the product, the Cartesian product there, is also just the bigger of the two. Of course, under the caveat that one is infinite and the other is not empty. Because if one of them's empty, then, well, anything times 0 is going to be 0. So I'm not going to prove this. This is something we could do at the end of the course if somebody is interested in it. We'd have to develop some tools we don't have. But anyway, so let me give you some examples of this worked out. This says things like, for instance, we already knew, remember z squared, this is the Cartesian product of z with itself. This is the size of the integers times the size of the integers. Well, now we know it's just the max of these two guys. And so that's the same as the size of the integers. Huh. So that's not, that's what we already knew. What if we did something like this? The real numbers and the integers. Well, we know that this size would be the maximum of the size of the reals and the size of the integers. And so considering that the reals contain the integers, we have an easy injection from the integers into the reals. So this is certainly, the reals must be at least as big as the integers, so that this must be the size of the reals, which we'll see later is actually strictly bigger than the size of the integers. Okay. But it also is the case that if we do something like union, or do a disjoint union of the reals and the integers, we would still get the same result, right? Disjoint unioning doesn't do anything. You also kind of get things like if you tack a finite set onto an infinite set, you haven't really added much of anything to it. All right. A few kind of other things before moving on to issues of being uncountable. I wanted to mention some other facts that are I think useful to know. We often like to focus on countable sets, and I'll just kind of mention, related to the above facts there, you can show that a countable unions of countable sets are countable. So in other words, if you have, say, all of these sets A sub I are no bigger than the natural numbers, then if we unioned all of those, a countable number of those up, we can show that this is also no bigger, oops, I'm using the wrong symbol. This is no bigger than the natural numbers. That's particularly handy. I'll kind of maybe explain why in just a second. Another thing is, if you take the collection, let's say we take subsets of A, but we demand that they're finite. Right? So this is definitely not all of the power set unless A itself was a finite set. And so this is a small collection in the power set, and you can actually show that the set, even though the set of all sets is always bigger, if you just take the set of all finite subsets, that is the, oops, I don't need less than or equal to there. That right there is always the same size as A. Well, I should say if A is infinite. So if you, for instance, if you take all, instead of the whole power set of the natural numbers, if you just took the set of all the finite subsets of the natural numbers, that would actually be still be a countable set. So why is this interesting? Well, it has some consequences, some other things that may not be obvious. Let me get rid of this. All right, so here's kind of consequences. What if we took real numbers and looked at polynomials? Okay, so this is the standard notation for polynomials with real coefficients. Okay, so we have polynomials with real coefficients. What I would like you to notice is one way to think about these guys is if you have a, let's say that you take a polynomial in here and its degree is n, then f is kind of like an element of r to the n plus 1, right? So if you take, because you can just keep track of what that polynomial is by its coefficients. So if you start to look at, let's make up a notation. Let's say that Pn is all of the polynomials of degree n, right? Well, then it's easy to see that the size of that should be the same as the size of Rn plus 1. But we know this is the size of R times R times R times R. That is the size, the cardinality of R raised to this finite power. But we also know from our cardinal arithmetic property right here that if you multiply, if you look at the size of, say, R squared, it's the same as the size of R. So the size of R cubed is the same as the size of R times R squared, which would still be the same as the size of R. And so by induction, we have that the size of the set of polynomials of degree n is the same as the size of the reals. Now, even better, what if we took this whole set here? You can see that that is a union of all of the polynomials of degree 0 on up. Well, also the 0 polynomial has no degree, but that's a single thing, so it doesn't really matter. Anyway, if we look at this now, we have a union of sets of size R. It's a countable union, and as an extension of what I said, a countable union of a countable set is countable. Turns out that a countable union of any infinite set is sets of size capped at whatever. It's going to be the same as the set, that size that we're capping this at. And so basically taking a union of countably many sets of size R isn't going to give you anything bigger. In fact, we're still going to end up with a set of size R. So maybe counterintuitively, it turns out that there are no more polynomials than there are real numbers. If you could restate this with the coefficients taken from the rational numbers, and so you would have that then we would be using our fact that the countable union of countable sets is countable. And so this collection of all polynomials with rational coefficients is countable. Even more so. There's this, and I kind of digress on all of this because I'm an algebraist and find this kind of interesting. If you look at, there's a notion of algebraic and transcendental, and then briefly, we say a number is algebraic if there exists some rational polynomial, a polynomial with rational coefficients, so R is algebraic, if there exists a polynomial with rational coefficients such that it's the root of that. So this would have to be a non-zero polynomial. Okay, so as an example, rational numbers are all algebraic, but also things like square root of 2 are. Why? Because if you take square root of 2 squared minus 2, you get 0. In other words, the square root of 2 is a root of the polynomial x squared minus 2, which certainly is a rational polynomial. So algebraic numbers, the collection of all algebraic numbers, is often denoted Q with a bar on top. This is called the algebraic closure of the rational numbers. This includes a lot of familiar things like, the cube root of 5 and stuff. You could add the square root of 7, right? These sorts of numbers are algebraic. It is not easy to prove, but it can be done. It can show that pi and e are not algebraic numbers. They transcend the rational numbers. Those are called transcendental numbers. Anyway, if you think about it, the collection of algebraic numbers is the same as the collection of roots of polynomials with rational coefficients. Each polynomial has, if its degree is n, it has at most n roots. And so basically what you're talking about are finite subsets of sets of rational numbers. Anyway, long story short, the collection of algebraic numbers is no bigger, in fact, it has the same size as the collection of polynomials with rational coefficients. And so one ends up with the result that the set of algebraic numbers is also countable, which means that anything that we're doing with standard kind of algebraic stuff, we're still sticking to a countable collection there. Another thing we can see from all of this, some more cardinal arithmetic stuff, is if you took, let's say that you took a set, like the real numbers, and you wrote it as a disjoint collection. I'm going to write it as the rational numbers and the irrational numbers. So by the way, a way of writing that would be R minus Q, right? That's this is all the things in R that don't belong to the rationals. That's what I mean by the irrationals. If you look at sizes, we know that from cardinal arithmetic, this is the max of the size of these two guys. But we also know that, so there's infinitely many irrational numbers. There's countably infinitely many rationals. Countable is the smallest kind of infinity. And so if we take the max of these two sizes, we must end up with the same as the size of the irrational numbers. And so what we just learned here is that there are as many irrational numbers as there are real numbers. So throwing in that countable collection of rational numbers doesn't do anything. Well, let's do this same argument over again with the algebraic closure. And so instead of irrationals now, I have the transcendental numbers. Maybe I'll call those T for transcendental. And so, well, if we go ahead and do that, we end up with, oh, sorry, this is not the reals anymore, because we can have complex numbers. Okay, so the complex numbers are a disjoint union of the algebraic numbers and the transcendental numbers. And so again, by that same reasoning, because transcendental numbers, there's infinitely many of those, although I didn't prove that. I didn't even prove there were any of them. But there's as many transcendental numbers as there are complex numbers. But also remember, complex numbers are pairs of real numbers, right? Real and imaginary part. And so that's the same as the size of R. So we just found out that there's the number of real numbers, complex numbers, transcendental numbers, and irrational numbers. These all have the same size. They are all, what that is called is a continuum, is their size. All right, now let's move on to our next topic, and namely, that is looking more at how big are the real numbers. And this is where things get really, really interesting. So first of all, let me give you two arguments to demonstrate that the real numbers are uncountable. Okay, here's kind of first line of reasoning. Well, the first way we can see this is to actually consider the fact, well, let me kind of show you a more general fact that if you take a set A, then let's take A to be non-empty, so this isn't weird. Then the power set of A has the same size as 2 to the cardinality of A. Okay. Now, we could ask, why is this the case? Let me give you a kind of a sketch of a proof. Take a subset of A. Then we can define a function as follows. This is chi sub B, and I'm going to go from A into the set 2, which is 0, 1. Okay. This is called a characteristic function. And the way we're going to define this function is we're going to say chi sub B of an element x, we're going to say it has an answer of 0, a value of 0, if x doesn't belong to B, and it's going to be 1 if x does belong to B. So another name for this would be an indicator function, right? So think of 0 as no and 1 as yes. In this function, you go, does x belong to B? And the function just either says no or yes. Okay. Now, conversely, if you take a function from A into the set 0, 1, notice that you could pick out, we could kind of define a function B to be the inverse image of 1. Remember, that would be all of the things in A. Too sloppy. So this would be all of the things in A such that f of x equals 1, right? That's what we mean by inverse image. It's all the, in this case, this would be all the things that map to 1. So without kind of going through the details of the proof, if you define B that way, you can show that f is exactly the characteristic function of B. Right? And so what I have sketched out here is that every subset gives you a characteristic function. Every characteristic function gives you a subset. And you can show that the relationship of subset to characteristic function, that in fact this is a bijection. And so that gives us that this is the same. That, by the way, if you take, if somebody says, hey, how big is the power set of, say, 1, 2, 3, we now know this is the same as 2 cubed, right? Which makes good sense. Okay, so if you accept all that, you can notice that, for instance, well, let's. I guess I don't need this for being uncountable, but let me kind of now circle back to explaining. Go back to the real numbers. Okay, so what do the real numbers have to do with a power set? All right, so first of all, I kind of mentioned that the real numbers have the same size as this interval of real numbers. I don't really want to get into all the ins and outs of this. Let me sort of justify, give you kind of a sketch and let you fill in the details. If you consider the function arctan, and let's say we take arctan of a real number, and we divide this by pi. Remember that the arctangent function takes real numbers and kicks out an answer that's between negative pi over 2 and pi over 2. So if we, let me do 2 over pi. Okay, so if we use this, and notice that this function is a bijection, right? You can see it's, well, I should be careful. If we define our function f by this, we get a bijection from the reals. Now I've scaled it, so this becomes 1, and this becomes -1. And so I get a bijection between the reals and the interval -1 to 1. And you can imagine by doing some sort of shift and scaling that you can now see that the real numbers, not only do they have the same size as this open interval, really the real numbers have the same size as any non-trivial open interval. And then tossing on endpoints, we know that taking an infinite set and adding 1 or 2 things doesn't change its size at all. And so in particular, you can see why this is the case. So instead of focusing on how the real numbers, we can now focus on just real numbers in this interval. Well, if you take real numbers in that interval, they look like this. We have, I'm going to write them out in kind of binary decimal. It's not binary decimal means 10, but kind of their binary expansion, right? If you take one of these numbers, you can write out the binary digits of it. By the way, what do we mean by that? I mean, B1 is times 1/2 plus B2 times 1/4, etc. And every real number in the interval 0 to up to 1 can be written in this way. And so we I'll say don't allow. Oh no, I killed it. So go away. All right, I bumped the power button. So let's see. Oh no, I was doing so well. So, all right, there we are, back recording. Let's not actually worry about. There's some details we can worry about, like having trailing ones. We don't. But anyway, you can see that if you take any kind of number in 0, 1, you can see that in this interval, you can see that as having a binary expansion. If I have all ones, actually, I would need to include one, right? 0.111111 indefinitely is the same thing as the number 1. Kind of like 0.99999 is nines repeated forever is 1. Anyway, think of each digit. This is a 0 or a 1 as being a no or yes. Right? In fact, let's re-index these. So these are b sub 0, b sub 1, etc. And so you can see that this guy is picking out a subset of the natural numbers. And so if you have a subset of the natural numbers, you can use that to take its characteristic function basically, and use the characteristic function as giving you. So let's take this guy, and then what you can do is build a binary expansion from this guy's characteristic function, where here's our first digit and our second digit, or bidget, I guess, and etc. And so you can see that the subsets of the natural numbers give us the same thing, a set of the same size as this, which is the same size as the reals. So this justifies why we will write that the reals have size 2 to the cardinality of n, or in other words, 2 to the aleph null. That is called the continuum. That's its size. So size of the continuum, again, is the same as the size of the power set of the natural numbers. And so we know the size of power sets is 2 that. And so that explains this notation. Okay. And now we can also see from that, we know that the size of a power set is strictly bigger than the set that you're taking the power set of. And so that justifies why the reals are uncountable. They're bigger than R. Let me show you a second, more direct but less instructive in terms of gives us less details. This is diagonalization. This is a huge trick that Cantor introduced in a very important technique for proving all sorts of things. So we just saw that the real numbers have the same size as various intervals. So let's say that we're going to again focus on the interval 0 to 1. Let's suppose that the real numbers could be listed off. So we could have x1, x2, etc. Right? Well, if we could do that, then we can write each one of these guys in terms of a decimal expansion. Okay. And we could make up some rules. So these are unique, right? So for instance, maybe I want to make sure that none of these decimals end in a trailing 9999. So again, I won't get into the details, but there's some things like that to worry about. So let's say that we've listed off all the real numbers, okay? Well, it turns out that our list can't possibly be complete. What we're going to do is take each guy in the diagonal, and we're going to, oops, wrong one. We're going to construct a new number. So let's let y1 be any digit that's not d11. So for instance, if d11 isn't, I don't know, 4, we're going to make it 4. Otherwise, if it is 4, we'll make it 5 or 7. It doesn't really matter a whole lot. But anyway, basically just make it different. We can do this in a very precise way. What we don't want to do is make it 9, so that we end up with a trail of 9s. But anyway, so if you want, in general, here's the formula. Yi, we're going to make sure that if if the diagonal guy, let's say, if the diagonal guy is, it doesn't really matter, 3, we're going to make this a 1. And if this guy is not equal to 3, we're going to make it 3. Okay. If we do that, now we consider this new number, y. Notice that this number it's a perfectly good real number in this interval. And if you compare it, notice that its first digit does not match the first digit of x1. So this guy definitely is not y. On the other hand, the second digit doesn't match this guy's second digit. We've rigged it up that way. So that's not x2, not x3. In other words, y is not in this set. So there's no way that we can list off, well, there's no way we can list off this interval, so there certainly is no way we can list off the reals. And so that right there, this is Cantor's diagonalization argument, just argued that the reals are uncountable. They can't be listed. I'll mention that diagonalization has important consequences other than just this. Maybe we'll talk about later what are called Turing machines. Turing machines are a kind of model for computation, pretty broad model of computation. In fact, the Church-Turing thesis essentially says that if you're doing computation, what you're doing is equivalent to running a Turing machine. Anyway, Turing machines can be encoded in a kind of countable way, and by using a diagonalization argument, you can show that there's no Turing machine to solve what's called the halting problem. So the same kind of argument shows that there are things that can't be computed. And maybe we'll come back to that later. So I'm going to kind of wrap up with pointing out some more stuff in this paper that I gave you guys. So the power sets are always bigger, we talked about. The reals are uncountable. There's the diagonalization argument right there. We didn't talk about ordinals. Cardinals are about size. Ordinals are about order. And I'd encourage you, if you're interested, go ahead and read this. It might make a great final project to dig into ordinals. Ordinal arithmetic is kind of strange. So we'll skip past all that. Cardinals we just talked about, and so now you can see things. By the way, omega here. Let me zoom so this is at the top. Omega is kind of a stand-in for the natural numbers. When we think of the natural numbers as an ordered set, as an ordinal, we call it omega. Anyway, if you look at omega plus 17, omega times 3, omega squared, we know these all have the same cardinality. Those are all countable. And we mentioned the natural numbers and rationals are countable. Now you can call, so just like you say Aleph null is countable infinity, Aleph 1 would be then whatever the next size is the first uncountable cardinal. And we can again figure out these simple arithmetic statements that, when you add, you take the max. So Aleph 1 plus 5 and Aleph 1 plus Aleph null, and etc. are all just Aleph 1. There's an explanation about functions and their relation to exponentiation. Notice here we have that the cardinality of the power set of the natural numbers is 2 to the Aleph null, which we call continuum. Notice that Aleph null, 2 to the Aleph null, 2 to the 2 to the Aleph null, etc. As we take power sets of power sets of power sets, we have a never-ending string of infinities. How about this? What if you consider when A is less than or equal to B, then obviously its size is less than or equal to A size is less than or equal to B size. So one can then easily see that if you take two cardinals, alpha and beta, in another cardinal gamma that alpha to the gamma is less than or equal to alpha to the beta if alpha is less than or equal to beta. And so we get this string, 2 to the aleph null less than 3 to the aleph null, which is less than or equal to aleph null to the aleph null part. Now here's the surprise. Notice that aleph null is actually strictly smaller than 2 to the aleph null. So you might think that top line there, that last inequality, should be a strict inequality, but actually we can't say that. What we definitely can say is there are no more functions from the natural numbers to the natural numbers than there are functions from the natural numbers to the reals, right? If you enlarge the codomain, you'll have at least as many functions. But hold up, 2 to the aleph null raised to the aleph null power is the same as taking 2 to the aleph null times aleph null. To explain that, if you have a function from the reals into functions from the reals to 2, which is confusing, or the natural numbers to the natural numbers to 2, it's the same as having an ordered pair of natural numbers mapping to 2. Anyway, if we kind of unravel that, then that says that 2 to the aleph null is the same as 2 to the aleph null times aleph null, but we know that multiplying cardinals, infinite cardinals, so you just take the max. And so this guy right here at the end, that's the same thing as continuum. And so all those inequalities actually are equalities. And so all of these things have the same, are the same size. That's, I think, kind of surprising. It's pretty cool. Another question. Another thing we could ask, as was thought to be true in the early 20th century, is 2 to the aleph null the size of the real numbers? Is this the next infinity after countable infinity? Seems like it ought to be true. Well, if you go and kind of press the matter, we definitely have that continuum is a bigger infinity than aleph null. So by definition, it's at least as big as the next infinity. But it turns out that the question is, are these two guys equal? This is something called the continuum hypothesis. That's the statement that those are equal. And as we've discussed in class before, this is one of those things that's independent from standard set theory. You can take that statement as true or false. Either way is equally consistent as with ZFC as a base theory. And so, by the way, if you, the generalized continuum hypothesis goes one step further and says, you know, we should always just make it that the power set of the kind of nth infinity size is the next infinity size, right? And if we did that, we'd know everything pretty much there is to know about cardinal arithmetic. We already know how to add and multiply. It's just the max function. So let's assume that exponentiation essentially is something well known, that exponentiation just takes you to the next size bigger. The general continuum hypothesis, if it were true, would, again, we'd know everything kind of there is to know about cardinal arithmetic, essentially. But unfortunately, even its base case, the continuum hypothesis, is in some sense unknowable from standard set theory. And then a little bit about this, the continuum hypothesis was conjectured, or not originally conjectured, but it was one of those things Hilbert brought attention to in his a famous list of open questions he gave in 1900. And it was Kurt Gödel who showed that basically you can't disprove the continuum hypothesis from ZFC, and then Paul Cohen showed that you can't prove it from ZFC either. And so maybe this is kind of food for thought to end with, namely that the real numbers, their size is continuum, and in some sense, set theory doesn't tell you how big that is. We know it's bigger than countable. We know it's uncountable. We have a name for it. We call it continuum, but we really don't know if it's aleph 1, aleph 2, aleph sub omega. You know, there's actually, there's ways to show that it's consistent with ZFC for the size of the real numbers to be almost any kind of cardinal you want. Not quite everything, but a lot. And so we really have no control. Our set theory has no control on how big the real numbers are. That means maybe the real numbers aren't as real as you thought they were. Anyway, I'll just leave you with that thought to mess with you, and encourage you to take a look at that paper, and we'll call that enough.